Okay, here we are. Welcome, everybody. Welcome to this new instance of the series of GReTA seminars. The talk of today will be given by Francesco Di Giovanni. Francesco got a Master of Science in Oxford a few years ago, and then a PhD at UCL. And then after a parenthesis in a company where he started working on machine learning and more precisely on graph neural networks, he moved to Cambridge, where he is now a research associate. So his main work activity is on neural networks, on graph neural networks, and he will tell us some new advances of his research. You can see the title on oversquashing and expressivity. Can graph neural network mix variables? So without further ado, I leave the spot to you, Francesco. Please.
Okay, thanks for the introduction, and it's been nice giving this opportunity to present this recent work. I realize now that this is not exactly what I had advertised or I had proposed in the past, but it was a few months, and then I thought, look, I don't have time to talk about two papers, so I'm going to focus on this one. This is the most recent. So this is joint work with Konstantin, who's just graduated his PhD at ETH. Then Michael, Bronson, Andrea, Mark, Sid, and Peter. So the paper is now on archive. There is actually a slightly more expanded version that I will hopefully post soon. So then let's start to go through it. I will begin by providing some notations, but I'm sure familiar with graphs are should be aware with that. So we have a graph which is made of nodes and edges, and let's say that we have n nodes, so n will denote the number of nodes, and we have the adjacency matrix that encodes the connectivity of the graph, right? So from now on, let's take the graph to be simple, so no multi-edges and undirected. We can, of course, compute the degree of each node, and we can stack all this information over the diagonal of the degree matrix. But now, in any graph machine learning problem we are interested in, we don't just have a graph structure, we also have features, right? So you can have different type of features. You can have node-wise features, edge-wise features, or even graph level features. In this talk, we will focus on node-wise features, which we can write as a map X that assigns a d-dimensional vector to any node of the graph. So you can basically represent these features as a matrix with n rows and d columns, and of course your implementation would take advantage of that. Now, because we are gonna discuss, graph neural networks or neural networks in general, we will have layers. So we will use this notation HVT to represent the hidden feature or hidden representation of node V at layer T. Okay. So graph neural networks is actually a very general class of models, and in fact, in my mind now, basically, a GNN is any neural network operating on a graph structure data, and by this definition, then even transformers adapted to graphs would be an instance of graph neural network. So let's try to be slightly more specific, and let's consider the family of message passing neural networks. So I will actually consider a slightly subclass of them, which is the one I can write down in the blue box. So I start from the input feature xv, and then I update the features of each node recursively through layers, so that at each layer T, the representation of the feature of node V is basically given by the action of a pointwise nonlinear map sigma. Then we have weight matrices omega and W, which can be, of course, different for each layer. And omega multiplies the node feature of V at the previous layer, and W multiplies the aggregation over the features of all neighbors. So how this aggregation takes place, we sum overall nodes that are connected to V. So this is why this matrix A here is typically a normalized version of the adjacency. And then we even allow a separate message function psi that takes as input the state of node V and the state of the neighbor U, okay? Now, you should probably see that this sort of form of message passing network is quite common. And in fact, many standard models like GCN, GraphSage, graph isomorphism networks, or gated GCN, in fact, take this form for certain choices of sigma and the adjacency matrix A and the message function psi. Now, I want to emphasize one point, which I will be coming back at the end of the talk. Right now, and in fact, throughout the presentation, there will be no assumption on the nature of the features. So what I mean by that is that even though I'm thinking that there is an underlying 2D graph, so to speak, the problem I'm describing can also be applied to point clouds in 3D space, where the adjacency matrix here is given by some, distance in Euclidean space or some cutoff radius, right? So there is no assumption on the nature of the features. The features can also, include positional information. So in fact, this is a very general analysis of message passing neural networks for geometric graphs, point clouds, or 2D graphs. The only, if you like, oops, sorry, this laptop is new for me. So the only assumption that somehow we make is that all nonlinear functions involved, so in particular sigma and the message function psi, will be taken to be twice differentiable. So we will see in a second why we make such an assumption, but I want to emphasize that this is by no means a strict requirement. So first of all, there are many smooth nonlinear activations for neural networks and in common libraries. So the tanh, arctangent, we have smooth versions of the ReLU, like the GELU function, we have the sigmoid. All of these functions are, of course, smooth. But besides a practical, the fact that in practical terms, there doesn't seem to be any difference between using a GELU or a ReLU, from a model-like point of view, that does make a difference. There are certain problems, think, for example, of neural PDEs, where the function we are trying to learn is not just continuous, and in particular, it's not just piecewise linear, as if we would use the ReLU activation, but it has to be smooth, right? It has to be more regular than continuous because it has to solve some partial differential equation. Or, for example, think of force field models where we want the gradient of the function we predict to be forces, so we have to be differentiable. And so this is just to convey the idea that this step of requirement is actually quite a mild one. It's not a strong assumption. Now, to make things slightly more concrete, I will be talking about graph level task. And in fact, let's assume that we have a problem that is a regression one, where for each attributed graph, we want to predict a certain output, which we take to be a scalar, like a real number. Now, in the paper, you can also, in the appendix, in section E of the appendix, you can also see all the derivations, all the theoretical results for node level task as well. So, but for simplicity, let's assume that we have this graph level task. So what we do is we take a message passing network for M layers, and then we apply a global pooling operation or a readout map. This is just a permutation invariant operation that basically allows us to associate a single vector to each graph. And in practice, this will either be the max, the mean, or the sum, so that the final prediction computed by the MPNN after m layers is just, in this case, a linear layer. So basically the inner product between some learnable weights theta and the output of this global pooling. So the output of this readout operation. Okay, so this was just a setup. Now, what about two problems that are mentioned in the title of this talk and the title of the paper, which are expressive power and oversquashing? Now, expressive power is a very simple, arguably the simplest question you can ask, in fact, about any neural network model, which basically means, what is my hypothesis space, right? Or put differently, what kind of functions my model can learn arbitrarily well, assuming I have found the right parameters, the right weights. Now, in the context of graph neural networks, there's been, of course, work in this scenario, and some earlier works have shown that graph neural networks can actually be universal, but this would entail either in practical architectures where you have to have tensors with rank increasing exponentially with the size of the graph, so basically just a theoretical work that is not useful in practice, or you have to break the symmetry of the graph by giving unique identifiers to each node. But arguably a much more common strategy to study the expressivity of GNNs is that of the color refinement algorithms or bispecific lemma algorithms. So the idea behind these algorithms is basically saying whether my GNN, or in any sort of model that I'm looking at, can separate the two graphs that are non-isomorphic. So basically, can I construct two representations that are different if the graphs that I've been given are not isomorphic? Now, despite there are some connections between looking at the separability of graphs and universal approximation of functions of graphs, it's fair to say that most of the research that has been done in this field, in terms of expressivity and bispecific lemma, has focused a lot on the graph structure and on this question of separating graphs that are not isomorphic, or separating nodes that are not isomorphic in the same graph. But this is arguably not what we care the most about in many applications. So in any scientific application where we have a point cloud in 3D space, the graph is actually not a physical property most of the time. It's just something that we rely on, typically by drawing some sort of abstract edges using the distance in Euclidean space and some cutoff radius. The majority of the information is in the either chemical features, if we have a molecule, for example, and in the geometry, so the positional information, so the positional features of the point cloud. So think of, angles, mutual distances, torsion angles, and so on. So the point is that we would like to address this question by actually studying expressivity in terms of characterizing which functions of the features are harder or impossible to learn for message passing neural networks of practical size. So we want to provide basically quantitative statements that say how expensive it is for a certain message passing neural network to learn a certain functions of the node features. And you will see in a second that this approach is, of course, quite different from looking at the separation of graphs from the point of view of the bispecific lemma algorithm, especially considering that most of these works, in fact, typically ignore the features and just look at the graph structure. The second problem is the one of oversquashing. Now, oversquashing has been first studied in the context of graph neural networks, at least by Alan and Yahav, who showed that mostly empirically, if you have the graph and you have a simple task where you want to effectively send information from a source node to a target node, then the model will most of the time fail to solve such a task as soon as the receptive field of the source node grows too quickly with the size, with basically the hop distance. Think of, for example, the case of a tree, like as a graph. So this was a kind of a high-level description, and several works, and I spent quite a bit of time in the last year and a half working on this problem, have tried to study formally what is causing oversquashing, right? But I think there is much less work, in fact, almost no work, I would say, before ours, that study how oversquashing affect the expressive power of message passing networks, and if we can measure it, right? In fact, when I describe oversquashing, I'm saying basically that there are certain functions, in the example of Valo and Yaha, functions that involve long-range interactions. So I need to exchange information between source and target that are very far away in the graph, that message passing network fail to learn. So this failure has to deal with the expressive power of our model. But what we argue in the paper is that using the traditional approach might not be the best one to understand what is causing this failure, how we can understand this failure. So this is why we want to propose a new way of studying expressivity that can ultimately also explain why oversquashing is a problem for expressivity and how this is happening. So I want to start with an example that is basically analysis one stuff, but is in the end what we can motivate the whole work. So suppose we have a smooth function, and let's say we have a graph with n nodes and that the features are all scalars, right? So if we have a graph functions of the features y, we can then think of this function as a function of n inputs, which will be the node features, and that as an output, there is just a scalar. So if the function is sufficiently regular, we can take the Taylor expansion of such function at some reference point. So we can write this function as a polynomial p of these n features plus some correction term, which will eventually also be a function of the features, but let's say we are close enough to the reference point. So this correction term is small. Now, if I'm asking how this function is mixing the information associated with the features v and u, which will, associated with the nodes v and u, which will be the features x, v, and xu, the first thing I can look at, because I have a polynomial p, is looking at the mixed products xv times xu and their powers in p. Now, mixing here is a terminology that basically means I'm looking at the type of product interactions between two variables, right? This is connected to effectively how, in a way, nonlinear, especially if I'm looking at powers, this dependence between xv and xu is with respect to the function y. But of course, this is not surprising. The lowest degree monomials, xv and xu, are multiplied by the hash term of such function at the reference point. So all of this very simple argument just to say that we can take the second order derivatives of a function of features on the nodes of a graph to estimate the mixing, or equivalently the product type of interactions between the node features xv and xu, okay? So in fact, let's fix this with a definition. So suppose we have a twice differentiable function on the graph. So this is a function of the node features xi. Again, think of the example where you want to predict some form of energy, and the features are, for example, chemical information and positional information of the atoms, right? Then the maximal mixing induced by such a function between the features xv and xu, it can be, we define it basically as the maximum overall input features of the maximal entry of the Hessian of y with respect to such features xv and xu. So the previous example was just to convey the idea, not surprising, that the Hessian of the function y, so the second order derivatives of y with respect to different features xv and xu, basically are a proxy measure of the type of interactions that the function has to account for between xv and xu. So by taking the maximal entry of such matrix and then taking the maximum of all input variables, we have a measure of the mixing that the function induces between the information or the features that we have associated with nodes v and u. Okay. Now, in practice, what we do have is not the ground truth function, which is this green y, which is typically what we do not know, but what we want to estimate the ground truth function with, which is the prediction of our message passing neural network. This is this y tilde. So the goal of this paper, in very brief terms, is studying the mixing induced by the MPNN prediction between two nodes v and u, and comparing it with the mixing required by the task. So the idea basically would be, if the mixing that a certain MPNN with a certain capacity can induce between two nodes is small, then the MPNN would not be able to model strong type of interactions between xv and xu, and therefore it will not be able to learn all of those functions that have such product type of interactions. So in a slide, we basically want to study second order derivatives and see and use them to see what kind of functions we are not able to learn in practice and why that's the case, right? So before I state the first main theorem of the paper, I'll try to start a bit more slowly with some intuition. So suppose we have a message passing neural network, and let's say that the features are all scalar. So the dimension is all one for each layer. So basically, we are saying we have some weights, which are now numbers, omega and w positive, and let's take the message function to just be a linear combination of the inputs. So it's very easy to rewrite the general message passing layer I had shown you a few slides earlier as the action of a pointwise activation sigma over these vector, which is just basically w times this graph operator s acting on the features of the previous layer. And this graph operator s is defined here. So basically, this is just given by, you have terms coming in from the message function, and okay, and then you have terms coming from identity because you also have residual terms. Okay, now because up to this sigma, basically the layer works by operating with such a matrix w times s on the previous features, you can convince yourself that the power k of ws is the matrix that controls how information is flowing over k layers. Or equivalently, the matrix ws to the power k is controlling how information is flowing over walks of length k in the graph. Now, suppose you have two nodes, v and u, and that the shortest walk distance between these two nodes is, say, r is 4. Now, if the depth m is smaller than half the distance, then the mixing induced by your MPNN between these two nodes will always be 0. So let's try to explain this very briefly. If the depth is smaller than half the distance, then there is no node in the graph that can receive information from both v and u. It will either receive information from v, because it's closer to v, or to u, or from none of those, but not from both. So this is basically what in literature is commonly referred to as underreaching, which is the easy case where if you don't have enough layers, certain parts of the graph will not even be able to communicate at all. Right. Now, what if we actually hit the boundary case? So suppose now the number of layers is exactly equal to half the distance. Let's say in this case is 2. So half the distance, which was 4. Now, what we can do, at least very naively, is trying to estimate the mixing induced at between V and U by looking at all the nodes I, which are equidistant from V and U, so they can now receive information from both V and U. And how I can estimate such information, I can look at the entry IV of the power M of my matrix WS. So I'm looking at how information is flowing over the path IV, and I'm multiplying how this information is flowing over the path IU, okay? Now, this is, of course, very sort of hand-waving, not too accurate, but the positive news is that this basically we can make this argument rigorous, even in the general case. So what we need is basically the following. We need to have a constant C sigma that is an upper bound on the derivatives of sigma, both first order and second order. Of course, this is always satisfied. All the nonlinear activations used in practice are smooth with bounded derivatives, so everything is good. Then we take omega and W to be the maximal norm, operator norm of the weight matrices, big omega and big W. Again, this is always satisfied in practice. Whenever we do training, the weight matrices will not explode, will stay bounded. And in fact, there are many approaches to even make such bounds smaller because we want to regularize the networks and keep the weight matrices small to prevent overfitting. And then finally, we also take for the same reason, basically, the gradients of the message function to be bounded, both the Jacobian and the Hessian, because we want to take second order derivatives, because of course we want to estimate the mixing, and the mixing was defined in terms of second order derivatives. And let's also be clear, most of MPNNs like GCN or GIN or SAGE, the message function psi is actually, the message function itself is actually linear. So these constants here will be basically all zeros but one. That would be one. So everything will be simple in many common cases, but we're trying to keep things general here. So the first result is basically deriving an upper bound, very general upper bound, on the mixing that an MPNN prediction can induce between the features associated with nodes V and U, right? So this mixing is a function of two things. It's a function of components of the architecture, so the number of layers M, the nonlinearity C sigma, the size of the weights W, but of course it is also a function of the graph topology, because both S, which is basically this operator here that I have defined, and Q, which is an operator that you can define recursively through S, it's not important here the exact form, are functions of the adjacency, so are functions of the graph topology. Okay, so we look at this bound and then we say, well, okay, but is this helpful? Because in this form, this doesn't seem that transparent. It's not super clear. First, how the architecture is contributing to the mixing, or which parts of the architecture are contributing the most to the mixing. And second, which properties of the graph topology affect the mixing the most, or if you like, how does the location or mutual location of the nodes V and U affect the mixing the most? So what we do is now assume, ignore C sigma. This is just because in basically any nonlinear activation we use, C sigma can be taken to be 1, but so for simplicity, we say, okay, let's say that C sigma is more or equal than 1, so we can ignore it. But it's super straightforward in any case to generalize all the results to arbitrary C sigma. So, and in terms of terminology, we say that the pair MW represents the capacity of the MPNN. So the MW, M is the number of layers, and W is the maximal norm of the weight matrices. So this pair now represent the capacity of the MPNN, or this is our terminology. Now, so far, we haven't really been talking about oversquashing, but this is where we make our sort of claim. Now, all of the previous works seem to suggest that oversquashing has to do with the inability of MPNNs to exchange information between different nodes, and therefore to model interactions between different nodes. So according to our intuition of, we use the Taylor expansion to motivate the mixing, why second order derivatives are a good proxy for measuring the mixing between different features, we propose a broader but more accurate definition of what oversquashing is. So given a message passing with a capacity MW, again, M is the number of layers, W is the maximal norm of the weight matrices, we say that the pairwise oversquashing between two nodes V and U is the inverse of the maximal mixing induced by the MPNN between the features XV and XU. Okay, so let's comment on this definition for a second so that hopefully I can convince you why it does make sense. First of all, why pairwise? So this is emphasized because clearly there might be forms of oversquashing that occur with multiple nodes, not just pairs of nodes. And you can see how the approach I've shown you so far can be generalized by looking at higher order derivatives or higher order terms in the Taylor expansion, if you like. So there is definitely room for building a hierarchy of oversquashing measures that go beyond the pairwise interactions here. So this is why we emphasize this is just for pairwise. Second of all, the measure we introduce is not just a function of the graph topology, or if you like, it's not just a function of V and U, but it's also a function of architectural components of the model, like M and W. And I think that makes sense because, of course, if we had a sort of an ideal architecture with infinite layers, infinite sort of dimensions for the weights, then we would expect that no oversquashing is happening. Everything is flowing regularly. So we want this function to also be accounting for components of the architecture. And of course, let's finally focus on the right-hand side. So why the inverse? So first of all, if the mixing is very large between two nodes, then it means that the MPNN is able to model strong interactions between V and U. So no problem in exchanging information there. We shouldn't be expecting oversquashing to happening. So the right-hand side should be small, which is the case. But in the other way around also works. So if the mixing is very small, so it means that the model with that capacity is not really able to exchange information between V and U, and therefore oversquashing should actually be strong there, which is motivated again by our choice of the inverse. Now, any definition has some form of, is somewhat arbitrary, right? So again, you can change this definition a little bit, and for example, take a decreasing function of the mixing, which is not the inverse, that would still convey the same message, right? But that's not the main point here. Now, computing the exact mixing in practice is not really easy, and theoretically, we don't really know exactly the second order derivatives of the MPNN. But now we can use the previous theorem, and because the previous theorem gave us an upper bound on this mixing, we can now derive a lower bound on this oversquashing measure, which we define as this tilde oversquashing. So in practice, what we will be doing in the following, and what we did in our work, is deriving lower bounds for these oversquashing tilde, which will ultimately lead to lower bound of the oversquashing measure. Okay. So let's summarize now the.
Sorry if I interrupt you.
Yes, sir.
Apparently, the slides are a bit cut on the right. And in the last one here, I don't see if the formula continues. I don't know if you see this on your laptop. You
mean this one?
On the right part of the slide is not visible. It's like if the slide is a bit cut. It was okay. This is better. So it's
Maybe
better.
this is okay. Then I need to control it a little bit. Okay, so
It was not. There was nothing not understandable before. Here, there was. This was just this point that I didn't know.
okay. I'll try to be clear, and I'll try to be careful then if there are equations or stuff on the right.
Thanks.
Okay, cool. Okay, so where we were here, right? So I think this is the slide that is sort of key in terms of understanding the whole strategy, the whole approach. So first of all, we have our definition of a squashing and our characterization of the proxy of a squashing. So a very simple consequence of that is that if we have a message passing a network that learns a function y tilde with a certain mixing, then the following inequality has to be satisfied. So in other words, a necessary condition for your model to learn a function with a certain mixing is that this inequality has to be satisfied. So the way now we phrase the expressivity problem is the following. We ask, what is the, if you are given a function, an arbitrary function, this green y, this ideally would be your task, right? So what you want to solve. This function will have a certain mixing. What we ask is the minimal capacity, MW, that is required to induce such a mixing. So in other words, we provide necessary conditions in terms of depth and size of the weights for an MPNN to be able to learn a function with a certain level of mixing. So in order to do that, we identify two cases. First, we fix the depth and we look at the norm of the weights. And in the second case, we take the norm of the weights to be nice and bounded, and we look at the number of layers as a variable that can change. Okay. So the first theorem is the following. So what we do, by the way, from now on, I'm taking the message passing matrix A to be the symmetrically normalized adjacency. This is just for simplicity, but in the paper, you can find in the appendix C and D extensions to of all the theorems to either common choices of the adjacency, like the random walk normalization or the unnormalized case. Now, consider the following boundary case. We have two nodes, V and U, and we take the number of layers to be half the distance, okay? So remember why this is a boundary case, because this is the minimal depth needed for your model to exchange any information between the nodes V and U. If the depth was smaller than this number, then you would have underreaching and no information whatsoever would travel from V to U. No mixing would happen. So let's look at this boundary case. Now, if we fix the depth to be at this boundary case, what we can do is we can show that a necessary condition for the MPNN to generate a certain level of mixing that I've written here down between V and U is that the norm of the weight or the maximal norm of the weights has to be growing with a minimal degree on the graph. So here C2, remember, is just a constant coming from the architecture and the derivatives. For example, for GCN or gene, C2 would just be 1, so you can ignore it. But what's interesting here is that in this simple case, we can show that a reason for why, for example, of squashing can be significantly worse on graphs rather than on sequences is that the norm of the weights or the capacity has to grow with the connectivity of the graph, which of course can be much larger than on sequences. But now this result is per se interesting, but it's not really what we need in practice, right? Because in practice, we never, first of all, we never really control the weights from below. We actually want the weights to be upper bounded, to be nice and small so that the training is stable and smooth. But from a theoretical perspective, we have several works that highlight how the size of the weights, like the spectral norm of the weights, so this little w here, is actually related to the generalization power of the model. So the larger this w, the worse the generalization can be, or if you like in more practical terms, you can get more easily overfitting if you have lots of weights, lots of big weights. So you don't want to increase the weight. This is not a viable solution. The more viable solution is getting the weights to be nice and bounded and increasing the depth, right? So ideally, you would say if I increase the depth significantly, but at some point I will manage to mix all the information I need. But now the question becomes, how significantly I need this depth to be increased. So this is, I think, that the nicest result in our paper. And so what we show is that if we take two nodes V and U, then a necessary condition for an MPNN to generate mixing between V and U as given here is that the number of layers has to grow with the mixing, of course, and these constants alpha and beta can be found in the paper. For simplicity here, I'm not writing them down. But more interestingly, the number of layers has to grow with the commute time between V and U. So remember, the commute time is a distance on the graph that measures the expected number of steps for a random walk to start at V, go to U, and then come back to V. So what this theorem is saying is basically the following. If you want to solve a task, and the task has strong mixing between two nodes V and U, but these two nodes have large commute time, then the number of layers has to be very large in order to generate such mixing, and in fact has to grow somewhat linearly with the commute time. But why this is now a bad result is because the commute time can be as large as, for example, the number of nodes to the power 3 for certain topologies. So in other words, a corollary of this theorem is on a graph with features. If you take message passing as in the theorem above, so with weights that are bounded by 1, nice and smooth, and the depth is bounded, let's say is smaller than the number of nodes, then you cannot learn functions that induce high mixing between features of nodes with large commute time. So this is the main theorem and the main result of the paper for a few reasons. So first, in a way, we have identified classes of functions that are harder to learn for message passing networks with practical size. So here we are saying that if we have practical size architectures, so the depth doesn't grow quadratically or even cubically in the number of nodes, functions that are heavily dependent on the interactions between nodes at large commute time will not be able to be approximated by your architecture. The second interesting point is that this result finally shows how oversquashing is effectively hindering the expressive power. So oversquashing can be thought of as the sort of disagreement between the task that requires strong mixing between nodes V and U and the graph topology, which instead assigns large commute time to nodes V and U. So it's this misalignment, task requiring lots of interactions between two nodes, and the graph topology, which instead puts these two nodes at places that are harder to get for random walks or diffusion processes. So as measured by the commute time being large. So this misalignment is more general than just saying oversquashing has to do with long-range interactions. We can sort of take the commute time as a good proxy for oversquashing, and it also brings back the task, right? It finally shows hopefully very clearly that the problem of oversquashing occurs when the task requires such mixing between nodes that have large commute time. If that's not the case, that's fine. You can have oversquashing between nodes and large commute time, but it will not be a problem because the task will not depend on it. A slightly subtle thing here is that it's been somehow implicit in all of these results, is because mixing in the end, these are just second order derivatives. What we are actually saying is that we have derived limitations on the derivatives of a message passing model to match the derivatives of a target function. So This again can be something we care about in practice if we have scenarios like neural PDEs, or we want to predict forces and things like that. And to the best of my knowledge, I haven't seen such a work achieving such conclusions for graph neural networks. So a work that shows actual limitations of a GNN, of the derivatives of a GNN function to learn the derivatives of a target function. And this is sort of implicit conclusion of our work, because if we now for a moment ignore mixing, ignore oversquashing, under the hood, what we are doing is trying to see if we can match second order derivatives of a GNN and second order derivatives of a target function. Okay, some comments here before I show you some experiments and then wrap up. So an important, I think, conclusion here is I hope you have appreciated how this approach to expressivity is very much different from looking at the Weisner-Lehmann test, or if you like, the separability of nodes or graphs based on their structures. In fact, throughout this talk and throughout the work, we had no assumption on the type of features. So the features can also contain very powerful structural or positional information. So the model we have looked at from the point of view of the Weisner-Lehmann test can actually be quite powerful if this structural encoding is structural information we have concatenated to the features is powerful enough. But this will not affect our results, right? And the reason is because we don't look at the ability of a model to separate node representations, which is an interesting question and can be relevant in different scenarios. But we look at a different problem, which is the ability of a model to exchange information between different nodes, whatever that information might be. And in fact, as I mentioned earlier, there is no, these results also apply to equivariant message passing models to, 3D point clouds, which are nowadays somewhat used in almost any application in AI for science. So hopefully what this also theorems are showing is that the way we exchange messages can be quite impactful if the task has some form of interactions between distant regions or regions that are poorly connected, right? So in other words, we can look at the commute time of the graphs we generate in the 3D space and see what the commute time distribution is to maybe get an intuition of whether this message passing graph is, this graph we generated is friendly or not to message passing. I'm gonna be very quick on this slide. I mean, this is just a slide just to emphasize that there are several general but also technical differences between all of these results and previous works in oversquashing. Most of this work is stuff I did also, so I'm quite familiar with it. But let me just say that the works are different on a technical level. None of the previous works have dealt with such a generality in terms of MPNN derivations, and basically no assumption besides smoothness and bounded weights, which is something that we all require. And previous sources have not made such a strong connection to expressivity and phrasing oversquashing as this inverse of the mixing, so to highlight that oversquashing has to do with the ability to mix features, and oversquashing can be mitigated by increasing the capacity of the model, but the extent to which such capacity has to be increased, of course, is something that one has to derive. And this nice connection between number of layers and commute time is novel. Another very quick slide showing that, of course, the theorems that I presented do not include all possible models. Notably, the theorems don't apply to attention-based models. So in principle, this is not a huge obstacle to overcome, especially for graph attention networks, but they make the derivation a little bit more technically involved. So I sort of decided to let this aside. But I think what's interesting is that the approach is very general. So you can now take this approach, for example, and study the mixing abilities of GNNs with different permutation invariant aggregations, right? Which are not necessarily like, for example, a sum over normalized adjacency. And one can argue or ask whether certain aggregations are friendlier or not in terms of the mixing abilities. Another, of course, realm of methods that I'm also quite familiar with is graph rewiring. So all of these works try to mitigate problems like oversquashing by replacing a graph with, or partly decoupling the input graph from the graph that is used in the architecture. Most of the current, most recent models now try to basically use both the input graph and sort of better one. But I think what's interesting is that some recent works, both in the context of GNNs, or I should say message passing models, and graph transformers, have argued that expander graphs are particularly good. Now, expander graphs are classes of graphs that basically are sparse, but also have sort of small commute time, roughly speaking. So I think it's interesting to see how our theory sort of back up these rewiring approaches, these strategies, because they show that that minimizing or reducing the commute time is actually a good strategy if we care about mixing information and avoiding oversquashing. Okay, I'm gonna finish then by showing some, I think, quite interesting synthetic experiments that we ran to validate our theory. So because in all of these results, we need, in order to validate the theory, we need to know the mixing required by the task. So because we need such information, we can't just take an arbitrary real-world data set and run some experiments there and draw conclusions, because we don't really know for certain what's the task there and how is the mixing that the task requires between certain nodes. So what we do is we took a real-world molecular graph, in this case, zinc molecular graphs, and we set all the features to 0 except for 2, which are uniform random numbers. And these 2 are sampled according to the quantile of the commute time distribution, so that we can basically control quite well the commute time between the 2 nodes with non-zero features. And then finally, the task is just a simple regression. So we have to compute a function with a nonlinear mixing of these 2 non-zero features. So just a quick note. On the left here in this sort of picture, you have one molecule in such data set, and we have colored the commute time of 3 pairs of nodes. Now, what I want to emphasize here is that clearly the nodes like the red ones, so nodes that are quite far away in the graph, we have a very large commute time. That is not surprising. But what's more interesting is that even nodes that are adjacent to each other, like the yellow ones, in this case, we can compute their commute time exactly as being twice the number of edges in the graph. And this is because the yellow nodes form a cut edge. So if a cut edge is basically an edge that if we removed it, then we would disconnect the graph. So what's interesting basically is that even nodes that are close to each other or even linked to each other may not struggle from oversquashing because their commute time is quite large. And of course, for a cut edge, this is easy to see, because if an edge is a cut edge, it means there are many more ways to for information to escape from that edge rather than being concentrated at that edge. So I just want to make this point because to further sort of emphasize that oversquashing is not just a problem of long-range interactions, and the commute time is a much better and finer metric. So first experiment, we considered 4 classical message passing models that are included in our theory. What we did was fixing the architectural components. So all of these models have roughly same number of parameters, 100K. And then we fixed the number of layers. I think it was 11 for this experiment. So to be sure that there was no underreaching. So any pair of nodes we identified could at least exchange information after 11 layers. But what we wanted to highlight now is, okay, since we're fixing layers, we're fixing parameters, we are roughly fixing the capacity of the model. Now, all our theory, put in simple terms, it's showing that the larger the commute time, of the two nodes whose information need to be mixed according to the task, then the larger the capacity needs to be for the MPNN to model such mixing. So what we expect, because the capacity is kept fixed, is that as we increase the commute time, the performance should deteriorate quite significantly. And this is what we observe, right? So on the y-axis, you have the mean average error. You can see how across all the models, such error increases, and basically sometimes even by order of magnitude as we increase the commute time of the nodes whose information has to be mixed according to our own task. The second experiment is sort of complementary to the first one. So in this case, we fix the quantile distribution. So we for each graph, we sample two nodes that are in the 0.8 quantile distribution of the commute time. So the commute time is quite large. And we look at all of these graphs. Again, we fix the number of parameters to be roughly 100K. And the idea is, for all of these graphs, I think a number of 7 layers would suffice to avoid underreaching. Again, 7 layers would be the minimal number of layers required to exchange information between these two nodes. But our theory is saying that for this task that has mixing between nodes at large commute time, the number of layers has to increase with the commute time. So it should actually be much larger than the number of layers, the minimal number of layers required to avoid underreaching. And this is what we validate experimentally, right? So you can see that the error goes down. In some cases, 30 layers is significantly better than 7 layers, even though the task only depends on information being exchanged between nodes for which 7 layers would suffice. So again, the theory I showed sort of back up this plot and justify why such a task can actually benefit from having twice, if not 3 times, the number of layers that should be required to have such non-zero mixing. Of course, one cannot push this, the x-axis to 100 or 200 layers, because as soon as you increase the number of layers significantly, there are many problems affecting trainability, stability, overfitting. Maybe there are issues concerning the vanishing of the gradients of the loss. So there is no point in going too large with number of layers, because otherwise you would have, the only way to make it work is basically having a lot of tricks that would affect anyway the theory or statements. And the final experiment was validating that if we fix instead the topology, so the commute time between the source and target, we fix the architectural components, but we change the task. So we change the mixing required by the task. For example, look at the first 2 rows. In the second row, the function we want to regress has a mixing that with an order of magnitude larger than the first row. We would expect that because we are not changing the capacity of the model, but we are changing the mixing required by the task, larger mixing would necessarily mean worse performance. And this is again validated across all the models that have a consistent degradation. They become at least twice worse, and this is further validated by the third row. Now, this is the end, really, but before I conclude, I want to say a few words on the current state of things. So, first of all, you can contact me, or you can contact also Konstantin, who's collaborator. In particular, he worked on the experimental side, and for any question. But I wanted to emphasize this, so, because we are at the end. So what's the current state of things? What's the current state of things for GNNs and oversquashing and all of that? There is in my opinion, quite a huge problem concerning graph machine learning, which is about evaluation. So we don't have a lot of benchmarks, a lot of data sets. Most of them are not good for different reasons. But even though there were efforts, recent efforts to introduce data sets that may be different from existing ones. They may have more interesting tasks, maybe tasks that involve long-range interactions. These data sets seem to have problems. So it seems to be more and more the case that to study the ability of certain models to capture long-range interactions and really test over squashing, we should go and look at point clouds or 3D graphs like large graphs like proteins, or the case of materials. So the case of 2D graphs, at least for the benchmarks we have at disposal right now, don't really seem to be good for any of these testing. Most of the tasks are like very sensitive to hyperparameter tuning. Even though those data sets where transformers were thought of being now more successful than MPNNs, turns out it's just a problem of bad evaluation. So I just wanted to highlight this because it's an unfortunate problem that not really affects the theory, of course, but it affects the testing this theory in practice in real world data sets. Okay, I'll stop here. And of course, I'm happy to take any question.
Thank you very much, Francesco. Very interesting talk. And so, is there any question, Raiko?
Yeah, thank you.
Yes.
Yes, thank you. Very interesting. So I, apart from anything else, I even learned something on the basics. Your kind of more generic MPNN model that I wasn't.
Raiko, I cannot hear you very well. Sorry.
Okay, so maybe sorry. Let me take the headphones away. Maybe is that better?
Much better.
Yeah. Okay. So yeah. So I thank you very much. I learned something new here. So I mean, apart from everything else, even the some of the introductions were kind of presented in a way that I haven't come across before. So that was a good way to catch up, I guess, on the latest terminology. So I guess I have two, maybe three questions or comments. So the first one is that obviously the kind of central notion that you introduced was the commute time.
Mm-hmm.
And I was trying to understand what that means in kind of more graph theoretic terms. I mean, obviously you introduced that for a quite specific purpose, but at the same time, it seems a measure of, I mean, something reminiscent almost of a distance measure. I mean, as you say, it's a sort of generalizing distance, which of course is a classic graph theoretic sort of concept, but there's also more, I guess, more recent things like in-betweenness and things like that, which are different, but I'm trying to understand whether the commute time can be something like a more, I guess, flow-oriented version of distance.
Yeah.
This doesn't take into account the capacity of the edges, but just the fact that there is an edge.
Yeah, I mean, I think so. I mean, I have to say, I'm not. Maybe, as I was saying before, like my background is on manifold, so maybe there were some classical work relating effector resistance to betweenness centrality. Most likely there was, but the point, just I can give you two comments on this. So the comparison with betweenness centrality. So the thing about betweenness centrality is that somewhat is looking at the if you look at two nodes, I mean, if you look at an edge, it's looking at the centrality of the edge in terms of how often effectively this edge is in the shortest path, for example, between two nodes. So that's, you would expect this metric to be somewhat aligned with the commute time, but the commute time is more general than that in a way, because it's not just looking at the shortest path, it's looking at all possible ways information is flowing on the graph across all lengths, random walk of all lengths. So the second comment, which is why I think the way I think about commute time, is that there has been, especially in geometric processing, I think seminal works in terms of diffusion maps, I think from 15-20 years ago, and the idea was you can to look at what are called diffusion distances. Now, diffusion distances basically are looking, it's somewhat you're looking at how if you're diffusing heat from a certain node, how much of this heat is arriving at the different node, or how quickly. And commute time is, I think of that as sort of a very much aligned with this intuition. The fact that you're looking at random walks, it means we're looking at diffusion process like the heat equation, propagation of heat on the graph. And you can think of this is a distance, and because it's looking at all possible walks, not just the shortest one of all lengths, what you would expect is very large commute time means that for heat to move from one node back and forth, it will take a long time. Instead, if you have very short commute time, then heat will go just fine. And of course, this is much more accurate than shortest path, because, for example, it's accounting trivially by if you have two nodes at distance 4, that doesn't mean anything. But if you have two nodes at distance 4 and small commute time, it means there will be many shortcuts, many paths of similar length that are connecting these two nodes. So yeah.
Okay. Yeah. So I'm just wondering whether one could make something. So whether that notion is useful in a wider context. So that's basically, as you say, if it's generalizing, or I mean, I don't know whether it's strictly generalizing, but if it's a conceptual sort of evolution of the notion of in-betweenness in that sense, taking into account more of the structure of the graph rather than just shortest paths. Then there are probably other applications for it in kind of flow-oriented problems on graphs. So, but that's basically what you just confirmed in the specific case of.
Yeah, I think so. I mean, also
geometry, isn't it?
Historically, I'm pretty commute time. I think it's much older because it's just so. Also, what's nice about commute time, I guess, under the hood, why commute time? Because one may ask, why exactly commute time? It's not right. It's not really a choice that I made, but it really emerged very naturally from the proofs, because basically once you start looking at this mixing and you start looking at sort of this truncated power series, there is a very nice power series representation of commute time, like this was from Lovas. And so because you have this very nice spectral decomposition of the commute time, this is the right object that sort of enters these bounds very naturally. It's not something that I forced upon. So which means this seems to be the right object to look at. But again, I would not be surprised if also something like betweenness and tight. I mean, anything that sort of captures these ability of sending information from two nodes and the centroid of an edge will play a role. Of course, certain quantities may be easier to deal with analytically, depending on the techniques used. But yeah. Okay.
Francesco, if I may add on this, so I think it's pretty natural to also, I'm learning a lot from your presentation because this is not my field of research, but I found very, very interesting some hints, some ideas that you presented. So from the perspective of looking at the deep neural network as a black box which analyzes a graphical structure in input, and according to certain magics that is inside, it looks natural that in a sense the kind what is relevant are not the distances between the nodes, but the overall something much more random, the way you randomly can go to a node to another, which clearly depends on the size of the graph. In particular, you say that for certain graphs, the commute time is in the order of the third power of the number of nodes, something like this, which is impressive. So this means that exactly the same topology in a small graph and in the large graph have completely different commute time if you take a snapshot of a graph. So therefore, the consequence is clearly that the difficulty of analyzing or extracting relevant information from graphs is dramatically affected by the size of the graph, I guess. And the question is, in your example, you have shown us a small molecule with about 12 nodes. What is the reasonable size for these graph neural networks? The size of graphs that are actually analyzed the graph neural networks. What is the order of magnitude? of nodes? You have any? Is there a precise idea, or this depends on the problem very much?
No, I mean what I try to explain also in this presentation is that oversquashing is a function of the model capacity, certainly. It's a function of the topology, but of the way, once you have such a quantity, say, you have to compare it with the mixing required by the task. So there is no way you can decouple any consideration from the task itself. And I'm going to give you like 2 examples. Why the molecule, for example, right? Because you can say, well, this molecule has whatever, 20 nodes or somewhat 20 nodes, 80 nodes, whatever. Now, the main, so one thing that I wanted to show here is that how does the topology matter and how does the task matter? So this graph would be clearly and reasonably ascribed as this is a small graph or in any capacity. So any GNN should be able to deal with it. Mm-hmm. The problem is that the reason why GNNs can deal successfully on these graphs in the original Zinc dataset is because the task is quite local. So the task will never really depend on in any way from exchanging any information between, say, the red nodes. In fact, even on such a small graph, the commute time between the red nodes can be quite large. And this is why, as soon as you change the task on the same graph, the performance deteriorates significantly. So the first thing is, it's very hard. There is no way, basically, of saying what's the minimum capacity granted if you don't know anything about the task. The second answer, just to give you an idea of why, also to back up why the task is important, in my opinion, if I have to be always completely frank with you, the real scenarios where pure 2D GNNs really work, are really needed in applications. Here I'm making a distinction. So 2D GNNs, I'm saying, I'm not talking about equivariant message passing on point clouds. I'm talking where you only have a graph structure and features. You don't have a point cloud. Are actually embedding huge graphs, like really huge, like think the YouTube graph, so billions of nodes and hundreds of billions of edges. But the reason why these GNNs work there, again, is because you're looking at a recommendation type of problems where it's very unlikely that you're going to need to exchange information between different nodes. You can actually look at very local portions of the graph, and this is going to work.
Okay.
But I want to also make another comment. Then what about, middle ground? What about proteins? You have maybe graphs of thousands of nodes. Maybe there are certain long-range interactions. Are we doomed? But this is, of course, where other smart techniques can enter. So depending on your computational budget, you may pay a price in memory and you can have a transformer. So if you have an architecture that now can seize everything at once, of course, you are bypassing this problem at the price of memory. Or you can try more interesting approaches where, you sort of move from local to global. Like, you take a coarsening approach, you take coarser resolutions of the protein. So you synthesize, and now you take smaller versions of it and try to exchange information across these smaller versions. So this is just to say basically that there is no strong recipe, even if you ask computational chemists or biologists, which I was attending a conference of them a few months ago, there is a strong debate between people that don't believe long-range interactions exist and people that actually say all the errors we have are because we are not accounting for long-range interactions. So it's even in a very specific real-world problem in chemistry or biology, defining long-range interaction, quantifying long-range interaction is never really a simple thing. So you always have to go by trial and error, and the task has to be accounted for. Otherwise, as you say, the same molecule can be very easy to deal with or can be problematic in terms of oversquashing.
Thank you for this explanation. It's crystal clear. Thanks a lot.
I have another question, which is somewhat related. So I'm trying to understand what are the engineering kind of consequences or sort of guidelines that derive from this. And I think I got the idea now to some extent, but maybe just to confirm that. So if you're trying to solve a particular problem, there's a characteristic of the problem, which is the mix-in. Okay, that measures the locality or otherwise of the problem. Okay, then you have the basically the commute time as a measure of how well the graph is able to deal with non-local sort of need with the need to gather non-local information. And if you take that together, well, what does that give you? It gives you something like a limit to the number of layers you need in your network. So it tells you essentially something about the architecture of your network in terms of at least in terms of the number of layers that you need in order to solve that problem, right?
Yeah. So in theory, this is accurate, the description. There is a catch though. So in the real world, you never really know the mixing from the task. So what you may guess, and this is what people do when they propose, for example, a new data set, and they say there are long-range interactions, and they try to provide some heuristics, some motivations for why that's the case, but there is not going to be a clear-cut answer, an exact measurement because of all the problems I said. So I think from my perspective, in terms of practical consequences of these terms, there are basically two. So the first one is that, well, I would say three. The first one is that the role of the depth has been maybe a little bit underexplored in the literature, because what these theorems seem to suggest, and even some simple synthetic experiments like this one, is that going much deeper may actually be very beneficial because of how the capacity has to scale. So this is the first take-home message. The second take-home message is unfortunately negative. It's very clear that if you have large graphs, or let's say larger than molecules, so let's say peptides, so small proteins, and you have long-range interactions or mixing induced between nodes at large commute time, the MPNN is not going to be able to solve it. So architecturally, this is not the right choice of model. So this is where you would need something else. As I said, either you go smarter, you try to work at different resolutions, or you go, okay, I have memory, I have compute, I'm going to use a transformer. The third answer is actually the more interesting to me, which is there are certain applications, in fact, many applications, as I was hinting at before, for proteins, materials, and where there is not really a graph, but you actually kind of compute a graph based on something like, I don't know, a cutoff radius, like every atom is connected to every other atom within this radius. Okay. But then what this, basically what you were saying in terms of commute time can be applied there, meaning because for those problems, especially on materials, we know, we think that there are long-range interactions because electrostatic interactions between different cells. The way we construct the graph matters. So one can maybe wonder, different constructions of the graph may lead to different commute time distributions. So one realization of the graph could be much friendlier to the message passing algorithm than another one based on their commute time. So this is probably an interesting practical take-home message, I would say, of all of this stuff.
So you want to construct a graph in that case that, I mean, it's basically commute time is something you want to optimize for in the graph construction, among other properties probably. But
so first of all, this could be one way, and there are already very classical algorithms that minimize it by redistributing the weights of the graph. Or you can change the graph a little, and this is where I mentioned very briefly that there are all these, again, very classical objects called expander graphs that are designed actually to be sparse. So you're not connecting everything to everything like a transformer. So you stay sparse, but the graph is designed in a way that any two nodes can be connected. Let's say there are no two nodes that have too bad of a commute time.
Yeah. Okay. Maybe related question. So they mentioned rewiring, and there was a obviously an earlier paper of yours that talked about.
Yes.
So that seems to be in a slightly sort of different approach to solve that problem in an engineering sense, isn't it? So if the graph isn't, let's say, if the commute time, I'm trying to connect to I'm not entirely sure this is true, but because I can't remember whether you talked about commute time there, but in today's terminology here, if the commute time isn't suitable for that graph, then you add edges to it in the right places to make it to improve it in that sense. So that is addressing the same problem, right?
Correct. So just to give you some context before I expand on this very briefly, the original paper, this was in fact my first paper that I did in machine learning, because I was coming from mining geometry, so I said, let's look at the curvature on the graph. So, and then you can, commute time is a better measure now, I would say, than curvature, because curvature is local, commute time is looking at everything. But in terms of, and from the engineering point of view, as you said, there are two issues here. The first one, as I mentioned, the benchmarks we have at disposal are not great. I'm not going to enter into the detail of that, but they're problematic. The second aspect is that maybe because of the benchmarks we tested on, but it seems to be the case that nice geometric rewiring approaches where you optimize and you add edges or you remove edges just to improve the propagation information might not gonna be the best approach. And I think the reason is, of course, so this is why most recent papers that rely on graph rewiring, they don't just add new edges, for example, and remove, but they sort of kind of like interleave the propagation over the existing graph and the new one, sort of they don't discard information from the input one. But I think there is a problem which it's not being studied yet, but I think this is what happens, is that if you have a graph, so my collaborator is a super smart professor at Stanford. He mentioned this to me, and this made a lot of sense. So some algorithm that may optimize for the commute time, because the commute time is global, is like you said, I have the road network in let's say in Europe, and I want to minimize the commute time. But if I don't account for any local constraint, no topology of the road network, the minimization, let's say I can only add one road that minimizes the commute time, it will give us like a road from Lisbon to Moscow, a single road. And of course, we know that this is not the best way because it's not accounting for the local traffic and the local geography. So this is what these algorithms end up doing most of the times. If you're only optimizing for something global metric like commute time, you're going to end up maximally screwing up the topology of the graph. So somehow you would like to account for both input graph, so local and non-local information, rewiring, graph transformer. And this is a strategy that in machine learning has been nowadays appearing most of things I look at, this idea of alternating local and global. So you want different lenses, basically, to look at information, but you want somehow the global to be conditioned on the local. You don't want just to maximize over something that ignores completely the local topology. So this is why the problem becomes not super trivial.
I was wondering about that in the sense that, I mean, from our point of view, from the graph rewriting point of view, the graphs are not that arbitrary, I guess, is the so the graph represents a structure, let's say a map, or molecule or something like that, where the edges are well defined and have a semantics. So just adding edges to that graph may improve some structural properties of it for the purposes of not propagating information, but it also changes the semantics of the graph. And obviously the question is, are you allowed to do that? So what is that? Isn't that a different problem that you're trying to solve rather than, so you're replacing one problem by another one, which is easier to solve, but it's a different problem.
Yeah, no, exactly. The idea is maybe that could be a good solution, depending on if you're simplifying the problem. But again, a transformer, ultimately, you can say you're connecting everything to everything. So the key, once again, is how you are storing information from what you had. So you had positional encoding, you have ways of recognizing what you had before. So that can, in principle, for example, an edge that existed in the input graph can be distinguished by a virtual edge that is being added because of other considerations. So that's basically the thing that now people do in different ways.
So you distinguish between edges that have semantics in the original data,
exactly,
and edges that are just there as propagators, essentially, of information.
Exactly. So this is why nowadays, I think we even had a recent paper about it, just to formalize this a little bit. But the graph rewiring can be now, I think, thought of as an example of multi-relational GNNs. So you have different weight matrices for different type of edges, and in this case, the type of edges would be edges that exist and edges that I'm adding, for example. So the model can, in principle, learn to distinguish them, at least.
Yeah, that makes sense. All right, excellent. I don't know. Unless there are any other questions, maybe we can,
I think,
finish the official part at that stage.
The official part, thanking again the speaker, Francesco, for this very interesting talk, and saying goodbye, and we can still close the streaming and remain just some more minutes, okay? And see you to the next seminar of the GReTA series of seminar, which I think there is one planned in November. There could be some other one before, because the situation is a bit fluid in this respect.
The next one on the list I can see is on comprehensive systems for software interoperability problems by Patrick Stünkel, and this is on the 15th of December. But we may
there could be some other one in the.
We could have. We're still sort of exploring if there's a space for having another one maybe in between there.
Okay, bye everybody, and I think the YouTube session can be closed.
Okay.